What the heck is a Rahn Repeat-O-Meter anyway? Welcome back to Ox Tools, I'm Tom. So in collaboration with John Saunders at NYC CNC, we're going to build a couple of Rahn Repeat-O-Meters and talk about some of the design points of this instrument. Just real quickly, that instrument is used to take repeat readings for finding local areas in flatness on surface plates and machine beds and things like that. Used in conjunction with some other tools, you can actually measure flatness with it. So kind of an interesting tool. So let's talk about it, and let's take a look at how the thing actually works and some of the design points related to its construction. So when you're measuring a surface plate, there's a couple things you have to do. There's an overall flatness, then there's a measurement called a repeat reading. And what that repeat reading does, you know, in general, this is a flat plane that's defined by a tolerance band of some width, right? But there may be actually small local errors that you want to know about. And the Rahn Repeat-O-Meter kind of finds those. Now, once you've actually determined the overall flatness of a particular plate, and you can't use the repeat-o-meter for that. Once you've established that overall flatness, you can actually transfer that reading with the repeat-o-meter to another plate. Okay, that's one of the beauties of that instrument. Okay, now let me just show you kind of how the thing actually works, and we're just going to simulate one because I don't actually have one, and that's going to change pretty soon. So the way it behaves is something like this, where you have an indicator. So you have a stable base, and the indicator is sensing something away from the base. So what we're doing is we're looking for local errors in the plate. Okay. Now, you really can't do it with an indicator, and not because they're not sensitive enough. It's because the stylus is so small. So it can find little chips and very, very tiny defects that really don't make any difference for the function of the surface plate. So normally what we would do is we would use a gauge block, something that has a little more surface area, okay, to help us with making those readings, okay. So what we would do is zero somewhere, and then we'd go check another place over here, okay, and then we go check another place over here, okay. Okay, so my index wasn't any good there. So this is actually kind of a tricky measurement to take, especially when you're talking about really small numbers, okay? And mechanical indicators, okay, that's better. Okay, mechanical indicators work, but this is not a stable platform. And what the Rahn Repeat-O-Meter does is it provides a really stable, thermally stable and mechanically stable platform to take these kinds of measurements. It's pretty robust. And let's take a look at one. Let's take a look at a picture of one, and we'll point out some of the highlights on these things. Okay, so I think it's time for a sketch. So let's examine the different areas of the Rahn Repeat-O-Meter. Okay, so it has a top bar. Okay, it's straighter than that. It's much straighter than that. Okay, and then it has a middle bar that this is basically a spacer. Okay, then it has the lower bar that's got the business on it. Like that, okay, all right, and then I didn't draw it in there but ahead of time, but it's got a little cut in it here, okay, like so, and then it has an indicator, like so, all right, and then the indicator comes through and touches that. All right. Now, the other thing that it has is it has an adjustment knob somewhere in this region here, like so. Okay, and another split like this. Okay, and I'll explain that in just a second. All right. So it has little feetsies on it. Okay, like so. And the way it behaves is if this is the surface plate that we're sitting on here, okay, we push it around on the surface plate, and this little guy right here, and let's take a look at a close-up of on the Rahn. Okay, and this behaves like a hinge. Okay, so the idea is there's a bunch of mass back here, and this part of the instrument is free to move up and down. Okay, and this is a stable platform for the indicator. So what we get is we're actually measuring little distances here. Okay, we're measuring little distances in that area. All right, now this little guy right here, it serves two functions. One is to zero the indicator, and the other is to actually take the indicator off of this contact point here so that you're not preloading the indicator. Now the other thing that, let's take a look, there's some links, some diagonal links. Let's look at those. Okay, and then so those links do this here, like so. Okay, and what those links do is they keep you from yielding this little flexure right here. Okay, so this is kind of a delicate little spot right here, so we can't have this just flopping down and hinging down on its own. All right, or else we'll damage that and then it'll break there and it's no good. Now these are loose. These links are loose, and all it is basically an over travel that prevents this from becoming damaged. Okay, so the key areas that we want to look at is we want to look at the feet. Okay, all right, we want to look at the feet, and then we want to look at the flexure. Okay, that's this guy right here. All right, and then we want to look at the links. Okay, those are the links. And then the other thing we want to look at is we want to look at what I'm calling the fine adjust. Okay. Now John has asked me to, just give this a pass through, from a designer standpoint, and offer some input to the instruments that he's building. He's going to actually do the building, so I'm going to give him some input, and then he's going to build some gauges, and hopefully I get to play with one. The first thing we're going to look at is the feet of the Rahn Repeat-O-Meter. Okay, and you saw a picture of the feet there. And what we really want in a foot on an instrument that slides on granite is we want the foot to be harder than the granite. Okay, so granite's reasonably hard. It's not super hard, but we want the foot material to be harder. Now, if we look at the bottom of an instrument like this, we have 4 feet on this guy here. And these have been, so this is hardened steel, and these have been ground, and then they've been lapped, so they're all in one plane. Okay, so these form a flat plane here that doesn't rock. Okay. Now you can use 3 points, and the Rahn has some of those features on the bottom as well. Okay, and 3 points is what we call kinematic, and it's the classic example of a kinematic system where if you have 3 points and they all bear and their positions are known, and if you remove any of them, it becomes unstable. Okay, so it's just the right number that you need. And it sits on any surface, and the feet bear on any surface. Whereas if you have 4 feet, if they're not perfectly in plane, they won't sit on a perfect plane, so you have rock. Okay, so three points are generally preferred for kinematic systems. Okay, so now this happens to have 4. The Rahn has 3 on one side and 1 out at the end of the measuring tool. All right, so what we want is we want these feet to be harder than the granite, and we want them lapped smooth so that it slides around the plate very nicely like this and doesn't chatter or drag or do anything obnoxious. Okay, so now the body of the Rahn is made out of mild steel. Okay, so what they've done is they've actually added some hardened bits onto the bottom. I'm not sure what they are, if they're just hardened steel or they're carbide or what. But there's a variety of things that you can plant there to form a nice sliding foot. John proposed the idea of using these little rest buttons. Those would probably be okay. They're a little thick in my mind. We want something that's a little lower. We want to keep this thing down nice and low, and we want a nice broad contact. Okay, so there's a couple ways you can do that, and one of my favorites is like what I did with this is I use balls. Okay, now these are carbide balls here that I've truncated, okay, and flattened, and then these have been lapped so that they're all in one plane. Now this one has 3, so no matter what surface it's sitting on, it's stable. Okay, so that's one way you can do it, and I prepared some samples here, and here's one. This is done with balls here. Now these are just ball bearing balls, 52-100 steel, and they were truncated and then ground flat on literally on a belt sander, and then surface grounded, get them basically planar, and then actually lapped. So these are nice and hard. These are 65 Rockwell, and they're cheap. Okay, a steel ball from McMaster Carr is $1 or something like that in this size. So these are also really easy to press into holes. This is just a drilled hole, and you just press it in, and I've drilled it all the way through so that you could knock it out if you wanted to knock it out. But that's a quick and easy way to make a really good foot system. Okay, and you can choose different materials. That's one of the beauties of this. This is steel. These could be carbide, they could be silicon nitride, they could be some other kind of ceramic, they could be bronze or brass or whatever you want, although those would not make good feet for this application. So that's one way you can do that. Okay. Another way is if you want carbide, okay, these are some old carbide inserts that I had, some square ones, and I don't particularly have a holder for square ones, but so I snagged a couple of 3 carbide inserts, and I just glued them down with Loctite 380. Okay, so I scuffed them up on some diamond, and I scuffed the steel underneath, so you can make a good bond there. Now you see the glue ran out. This one I kind of trimmed away a little bit to make it a little neater, just to illustrate that you can do that. And these will be on there pretty good. Okay, and if you knock one off, you can put one back on. But this Loctite 380 is pretty good. And then that was also lapped. So this makes a nice slidey surface as well. Okay, and then I got one more that I prepared, and which is along the lines of this. But what I did was I had some round carbide inserts that actually had a mounting hole through them, and I said, oh, okay, well, let's just do that. And so there's a kind of an easy way to recycle some old carbide inserts if you have some round ones around that have a hole through them. Okay, and once again, those were lapped, so they're all in the same plane. Okay, all right. So that's a couple ways you can do feet. My personal favorite is this one, just because you have the choices of different ball materials, and balls are dirt cheap, and they're relatively insensitive to how much press fit you have in the hole. Okay, in fact, this is believe it or not, that's a 15 thousandths of an inch press fit in that. It's just a drilled hole that's 1 15 thousandths smaller than the diameter of the ball, and I just press it in the arbor press, and Bob's your uncle. So they're relatively insensitive to the hole diameter, mainly because they're only at the maximum diameter at the equator, so it's a very small surface area that's in contact, so it tends to swage the steel and push it out of the way really easily. So, okay, and that's really simple, but getting them aligned can be a little bit tricky, and you kind of get one chance at that. So, okay. So anyway, there's feet. Let's talk about the Flexure next. Okay, these are flexures here, all right? And what a flexure is basically a piece of material that flexes, okay? So it behaves kind of like a hinge, but it's basically frictionless, okay, which is one of the beauties of flexures, okay? So we have one in here, and then the way it behaves is when we make this adjustment, this is flexing this flexure that's in the front. And this is made out of blue tempered spring steel, so it has a large elastic range, okay? This is a fine adjust here. This is basically the same system here, a little different, basically, kind of the same deal, okay? So the Rahn Repeat-O-Meter has a flexure in it as well, okay? Now the problem with the Rahn is that it's made out of mild steel, okay? Now this is mild steel here, and this is spring steel here, okay? And I didn't quite have the same thicknesses, but for this illustration is probably okay. So spring steel is it has the same stiffness, okay, the same modulus as mild steel does, okay, but it has a larger elastic range because it's stronger, all right? So so it can take more strain, all right? So the example here is, if I hold this down, I can push this all the way down to the surface plate, and it returns to its original shape. So this is we're still in its elastic range, all right? So that's the spring steel. Now, if we take the mild steel, it also has an elastic range too, but I can tell you it's a lot less. All right. All right. So I'm in the elastic range, but if I go all the way down, well, actually I didn't quite make it to the. Well, it did. It bent a little bit. All right. So the material yielded. So we exceeded its elastic range. All right. So you can see it's got a little kink in it now, okay? So, right, if I flex it, and I flex this kind of the same way, it returns, all right? So spring steel makes a good flexure. Mild steel behaves the same way over a smaller range, okay? That's the point I'm trying to illustrate here. The mild steel behaves exactly the same, but the range is smaller. So with the Rahn, it's made out of mild steel, so that little flexure really can't move very much, all right? And that's what the links do. They protect that flexure from yielding, right? So if we didn't have those links on the side, it would just bloop, and it would just bend, yield, all right? It would yield plastically, all right? So that's how that flexure works on that, and that's kind of basic flexure behavior there. And they're just a wonderful device that you can apply in all kinds of mechanisms, and if you're clever. All right, so let's talk about the links next. All right, we talked about the feet, we talked about the flexure. Let's talk about the links next. That's these guys right here. Let's get a new piece of paper going here. Okay, so what we're trying to do, let's see here, let's draw this thing. We got a little cut like that. Okay, there's actually a little bit more material left in there, and you can see this is, it's cut most of the way through. It's weakened, and the idea is that this can move in a little arc like that, okay, hinging around this point right here, okay? And that's the flexure. All right. So the links, and we'll just draw our next block on here. And I don't remember. Yeah, I think they go all the way up to the all the way up to the top piece here. So there's a tapped, actually a pinhole here and a tapped hole here, like that. Okay, and the links loop around here like this. Okay, so this end is fine. It's basically just pivoting on a dowel pin there. This is the end that we have to do something with right here. So our link, make sure I'm not out of the frame here. Our link is like this, and it has a hole through it like so. Okay, and it has some thickness like that. And we don't really care about this end here. So this is the hole in the link. So what we want is we want something that behaves like a shoulder bolt. Okay, but we want a little bit of clearance in that. So if we draw that in section view here, all right, here's our link. And once again, we don't care about that. So we got a hole through here. This is our base plate here. We've got a tapped hole. Okay, tapped hole. So what we want is we want a liner or the pivot to be just have a little bit of clearance radially, okay, and this is the wiggle that allows you to take the measurement, okay, but the other thing we want is we want it to have a little bit of extra thickness. Now I'm kind of exaggerating it here, okay, and then it'd have a clearance hole through it like that, okay. So it wants to have a little extra thickness, so when we put the fastener, okay, we'll say it's a slotted fastener, this link is free, it's not trapped on its thickness. All right, but we can still tighten the screw up. You don't want to have to leave the screw loose or something silly like that. So this little bushing, and it's just a little bushing like this, okay, looks something like that. That thickness, T, okay, is the link plus 10 thousandths or something like that, okay, and then it has a hole through it that you can mount it to. So you can mount it to this lower section here. Excuse me. Okay, so the links are just going to be plain steel. This I would probably make out of probably brass, something simple like that. That would probably be fine. And then I'd use something, a large diameter screw head, okay, so that the whole thing is captive and then you can tighten it down. So something like a truss head, okay, and a truss head is, it's hard to tell where I am. I'm sliding off the paper. A truss head is kind of a large diameter head that kind of looks like that. Okay, and then you have this screw body there. All right, and it can be a slotted or a Phillips or a hex drive or something like that. So the ratio of a truss head, the ratio of the head diameter to the thread diameter is large. Okay. So that kind of covers the links and what needs to happen with the links. This can be close fitting, but it just needs to, it just needs to slide on and off of there pretty easily. And then one screw retains one link. All right. So that's the links. We talked about that. Now let's talk about the fine adjust, because there's a lot of room for improvement on the Rahn with this kooky fine adjust that they have on there. Okay. All right. The last thing we want to discuss is the fine adjust on the Rahn Repeat-O-Meter. So let's set this aside for a sec. So what Rahn did, and it's not a nice system. It's kind of clumsily done. So this upper plate, what they've done is they've taken a saw cut down it, all right, like so. And I'm just going to exaggerate it a little bit like this. And it's not even that nice, okay? It's just a nasty saw cut, all right, like so. And the indicator mounts here, okay, and projects through like this, all right. And then they have this fine adjust mechanism here. That's got some it's got a bushing that goes in here, and it's some kind of weird, it's got a weird dual thread setup or something. I'm not even clear how it works. It may be a differential thread or something like that. And it's all done through this saw cut, all right? So, which makes it kind of a pain in the neck, all right? And you can't really apply a good idea to it. So what I would propose instead is that we do something like this. All right, is we just separate those two functions, right? Actually, all right. And then what we're going to do is we're going to add another piece in. Okay, so we're just going to separate. We're going to make, instead of making it monolithic, we're going to make it one piece and we'll make it two piece, right? Like so. Okay, this will just mount with some little counterbore screws in here. Okay, and now we can do whatever the heck we want in this area because we have room to work because it's two separate pieces. All right. For example, this is a little system that I did, and it's a piece of tubing. It's one piece, and what it's for is it's for shortening screws. So what I can do is unwind this, and the jaws open up, and you can get the screw out. Okay, you know, if you've ever had to shorten screws, it's a pain in the you know what. Okay, so here I can crank it down, and this is threaded, so I can tighten this back up, and it locks down around the screw, and I can just belt sand this off and then drop it off, drop it out and put another one in, and I don't have to screw it all the way through. Now the way this works is it's got a plain hole through, just a straight hole through this wall, and then this wall is threaded here. Okay, so we have a lock nut on this side, so this knob and screw basically kind of idles in this one side. Meanwhile, it's threaded in this other side, so it pushes and pulls this side of the clamp. Okay, so this is acting like a flexure that we talked about, right? So let's do it here. Let's go ahead and do it. So, and you see it's just idling there, right? And I open it up, and the jaws are opening up. Well, that's exactly what we want to happen here, right? So let's do that. Let's put a counterbore in here, and then we'll put a plain hole through here like this. And then we'll just put a threaded hole there, okay? So now Mr. Knob sits here, okay? And then we have a lock nut on this side, and Mr. Stud goes through into this lower part, and it all goes together. So when we turn the screw, this lower part just follows the screw, okay? And that's just what we want to happen, okay? It's pushing this away. All right, it's lifting the indicator off of its rest here that's attached to the lower member. All right, so very simple, all very simple operations. It allows, you know, us to mill these features. Okay, actually, this little step ends up being pretty tiny because we just want a little crack, little space through there. Okay. Allows us to mill this surface and make it real nice. We make this piece separate. It's all lovely and happy, and now we can put a proper functioning kind of fine adjust in there. You know, and I'd make this something like you know, quarter 28 or something like that. You know, 1032 would probably be okay as well. It doesn't particularly need to be a super fine thread, okay? Believe me, with flexures, you can have a fairly coarse thread and still be able to adjust the indicator and null the indicator out. All right, so that's Tom's 2 cents worth. Two cents worth on the fine adjust. Cutting this flexure is probably the last thing that we should have a little discussion about. That's this angled cut that comes in like this and actually forms the flexure down at the bottom. So it's an angled cut, probably, actually, you know what, that's a good question. I don't know why it's actually angled, but if we prop this up at an angle, we can access it with a nice slitting saw like this. This will produce a nice precision narrow groove and allow us to control that the amount that's left down at the bottom really nicely. If you just use it, if you do it on a bandsaw, sure it'll work, but you know, there's a possibility that you can get that cut tipped a little bit, and the flexure would be thicker on one side than the other, and it might behave a little bit funny. This allows us to kind of do a nice job of it, since we're kind of fussy guys. This is 1/16 thick, about 1.5 millimeters. The slot could be anywhere from 1 millimeter to 3 millimeters, and everything would function normally and be fine. This is a little pallet, and this is the mini pallet. And I know Mr. Saunders has his own version of this, so this is a good way to hold this, and this will be the last operation. You're going to have all your tapped holes, you know, all your tapped holes are going to be in here. The little feetsies will be installed, everything will be done, and this is really the last thing. And you could actually do the assembly on top of this, if you were so inclined. You can pop this out, and now this thing sits on the table, and we can just build the instrument up right off of the bottom after we cut that slot. So that's kind of how I would attack that one. The last thing I want to talk about is how the indicator actually mounts. You know, there's a variety of different indicators that you might want to put in your Rahn Repeat-O-Meter copy, and so there's some pretty wild variations in the shank diameters. All right, and we're going to show some examples of what you might find. You know, this is 8 millimeter, I think, and then you have 3/8, which would be your kind of normal indicator shank here, right? But in the range, in the resolution of a mechanical indicator that you would use on the Rahn Repeat-O-Meter, we're looking for something in the 10 to 20 millionths, okay, range, okay, a mechanical indicator. So there's limited choices. You got the CEJs, you've got the Mars, Karl Marr, the Millimesh, and Supramesh, and CEJ, what else? And then you can also go to electronic gauging, which is what I plan to do. So now the lesson here is that you should just leave the door open to put whatever you want in your Rahn Repeat-O-Meter, and leave the door open so that you can upgrade. Okay, so instead of just putting an 8 millimeter hole through, what we might do is in the top plate here where the indicator mounts, let's say this is the spot that you want the indicator to mount, right? All right, so let's just leave the door open, and so we'll make a little clamping mechanism here. All right. Let's make it look swoopy and nice. All right. And then we're going to leave a large, oops, let's do this. We're going to add a little relief hole, okay, and then a cut. So we have a fastener that goes through here, okay, and that clamps around a bushing, all right, that you put your smaller hole in, okay? This doesn't have an eraser, so do I have an eraser? Yeah, I don't have an eraser handy. Okay, so what you're doing is you're bushing this down to whatever size indicator that you might want to put in there. So the maximum would probably be one of those big CEJ type indicators that have a very long shank on it, and they have the necessary resolution. So what I would do is leave that hole large and just bush it down and make interchangeable bushings to whatever you care to make, okay? And then your fine adjust is back in this area here, okay? Something like that. So that would be the profile of the top plate, and it allows you to put some nice curves in there to make it look nice. And the newer Rahns have this ability too, so they've already thought of that, so that's nothing That's nothing new. It's just an observation on my part that makes sense. Is make it big. It's easier to make it smaller. So if you have all this thing and you get it black oxided coated or polished or whatever, you're not going to want to take it apart and bore a larger hole in it to put a different kind of an indicator in it. Okay. So just do that up front. That's all I'm saying. All right. Actually, you probably have some little radiuses in there too. Okay, just to make it look nice. That's what I do. So anyway, guys, that's Tom's 2 cents worth on the Rahn Repeat-O-Meter, and I hope you like this. And go check out John's video, and there's a link at the end, and you can go straight to his video and check it out. And John's gonna incorporate the design elements that he likes the sound of, and build a couple gauges, and we're gonna or a couple of repeat-o-meters, and we're gonna play around with them. We'll go ahead and check surface plates. We'll do some other stuff with them. Thanks for watching.